Our galaxy is moving.
Astronomers measure the motion across radio sky maps. It should not be moving this way. Motion surveys track nearby galaxies sliding in the same direction. Clusters follow the same path across the maps. The pattern grows larger with every measurement. Radio telescopes reveal a wall of stars ahead. The region blocks direct observation, but the motion continues behind it. Hundreds of galaxies stream together across the sky. The entire local region drifts the same way. Gravity should scatter the galaxies. Instead, they accelerate together. Something enormous is pulling our galaxy forward. Astronomers first assumed a simple cause. Perhaps a nearby cluster was pulling the Milky Way. But deeper velocity maps revealed a far stronger motion. Entire galaxy clusters drift the same direction. This is not the movement of a single galaxy. It is the motion of a vast region of space. And astronomers still cannot see what is pulling everything inward. Look outward from Earth and the Milky Way appears immense. Hundreds of billions of stars form a rotating disk around a dark center. Gas clouds drift between spiral arms where new stars ignite. For centuries, this system seemed like the whole universe, a vast rotating island surrounded by darkness. Modern astronomy changed that view. Beyond the Milky Way lie other galaxies scattered across deep space. Some are spirals like our own, while others glow as smooth spheres of ancient stars. The Milky Way belongs to a small gathering called the Local Group. Several dozen galaxies share this region of space. Two large spirals dominate the group: our own galaxy and the Andromeda Galaxy. These two systems contain most of the mass in the neighborhood. Each holds hundreds of billions of stars. Gravity binds them together across millions of light years. Around them drift smaller companions. Dwarf galaxies orbit like faint satellites. Some are stretched by tidal forces as they circle their larger hosts. From this perspective, the structure feels stable. A small family of galaxies slowly interacting over immense time. Gravity pulls the members together. Orbits shift slowly, but the system remains contained. Yet the first careful velocity measurements hinted at something unexpected. Astronomers began to measure how fast galaxies move through space. They used the stretching of light to determine motion. Light from objects moving away becomes redder. Light from objects moving closer becomes bluer. This effect is small, but measurable. Each galaxy carries a faint signature of its motion. When these measurements were first applied across nearby galaxies, the results seemed ordinary. Many galaxies drifted outward as space itself expanded. This expansion had already been discovered through distant observations. But closer to home, a different pattern appeared. The galaxies of the Local Group were not simply drifting apart. They were moving together. The entire group showed a shared motion through space. Not a gentle drift, but a steady current. The direction was clear. The speed was immense. Astronomers compared the motion of our galaxy against the cosmic background radiation. This faint glow fills the universe from every direction. It is the cooling light left from the early universe. In a perfectly still galaxy, that radiation would appear uniform across the sky. The temperature would be the same in every direction. But it is not. One side of the sky appears slightly warmer, the opposite side appears slightly cooler. This difference is tiny, only a few thousandths of a degree. Yet it carries a powerful meaning. The Milky Way is moving through that ancient light. As the galaxy moves forward, the radiation ahead is compressed slightly. Behind the motion, it stretches. The pattern reveals the direction of travel and the speed. Our galaxy moves through the cosmic background at more than 600 kilometers per second. That is over 2 million kilometers every hour. The entire local group shares this motion. Dozens of galaxies are moving together through space. A small cluster traveling through the larger universe. At first, this seemed reasonable. Gravity within the local group could explain shared motion. Galaxies pull on one another through invisible halos of dark matter. But the direction of motion raised questions. The local group was not drifting toward Andromeda alone. It was moving toward something much farther away. The motion pointed beyond the boundaries of the group, beyond the nearest clusters of galaxies. Something larger was influencing the path. To understand this motion, astronomers expanded their measurements. They mapped velocities across wider regions of space. Hundreds of galaxies were studied, then thousands. Each galaxy carried a small arrow of motion hidden inside its light. When these arrows were plotted across the sky, a pattern emerged. Galaxies across enormous distances were drifting in the same direction. Not perfectly aligned, but clearly guided. Like leaves floating along the same river. The Milky Way was not traveling alone. Entire clusters were moving together. Gravity was shaping motion across a region far larger than the local group. And the deeper the measurements reached, the clearer the direction became. Everything pointed toward one region of the sky. A region hidden behind the dense stars and dust of our own galaxy. In that direction, something enormous waits. A gravitational center powerful enough to pull thousands of galaxies. The motion of our galaxy is only one small part of that larger flow. Gravity reaches across cosmic distances, and the current is already carrying us forward. To understand what is pulling the Milky Way, astronomers had to measure motion across a much larger region of space. Individual galaxies move in complex ways. Each galaxy spins. Each galaxy interacts with neighbors. Small gravitational encounters can change direction slowly over time. But beneath that local complexity lies a deeper pattern. Large regions of the universe move together. Astronomers call this motion peculiar velocity. It is the motion a galaxy has beyond the simple expansion of space. The universe itself is expanding. Distant galaxies move away as space stretches between them. This expansion follows a predictable rule. The farther a galaxy lies, the faster it recedes. But peculiar velocity is different. It is motion caused by gravity pulling matter toward regions of higher mass. Gravity bends the flow of galaxies. To reveal this hidden motion, astronomers needed two measurements: distance and speed. Speed can be measured from light. Distance is much harder. For nearby galaxies, astronomers use special stars that pulse with steady rhythm. The brightness of these stars reveals how far away their host galaxy lies. Other methods rely on exploding stars. Certain stellar explosions shine with nearly identical brightness. By comparing how bright they appear from Earth, astronomers estimate their distance. With distance and speed combined, a deeper map begins to appear. Imagine the universe as a slow-moving ocean. Galaxies drift across its surface. Expansion pushes them outward. But gravity creates currents. Some regions attract matter strongly. Other regions contain less mass and exert weaker pull. Galaxies respond to these differences. They drift toward deeper gravitational wells. When astronomers mapped the motions of hundreds of galaxies, something remarkable appeared. The local group was not simply moving toward a nearby cluster. It was flowing along a larger current shared by many galaxy groups. Clusters of galaxies across tens of millions of light-years were drifting in nearly the same direction. The pattern looked less like random motion and more like a river system. Gravity pulls inward.
Galaxies follow.
The Virgo cluster became the first major landmark in this cosmic flow. This cluster lies tens of millions of light-years from the Milky Way. Thousands of galaxies gather there. The total mass of the cluster reaches many hundreds of trillions of suns.
For a time, astronomers believed Virgo might explain the motion. Its gravity is powerful.
The local group is indeed drifting slowly toward this cluster. But measurements continue to expand outward, and the deeper the map extended, the clearer the problem became. Virgo alone could not explain the motion. Galaxies beyond Virgo were also drifting in the same direction. Clusters on the far side of Virgo moved with the same general flow. It was as if Virgo itself was being pulled. The current did not stop there. The deeper measurements reached, the faster galaxies seemed to move along this direction. The velocities increased across hundreds of millions of light-years. Gravity on this scale requires enormous mass. Not a single cluster. Something larger. Astronomers began to measure motion across entire superclusters. These are vast assemblies containing thousands of galaxies. When their velocities were plotted, the pattern became unmistakable. Galaxies across a region spanning hundreds of millions of light-years were drifting toward the same hidden destination. The flow lines converged toward one location in the sky. A region located behind the thick band of the Milky Way. Here, the problem grew stranger. The Milky Way blocks our direct view in that direction. Dust clouds filled the galactic plane. Billions of stars shine in front of distant space. Light from distant galaxies struggles to pass through. This region became known as the zone of avoidance. Not because galaxies are absent, because they are difficult to see. Behind that curtain, something massive was shaping the motion of thousands of galaxies. The flow of matter pointed there again and again. Measurements of velocity confirmed it. Clusters drift inward. Galaxy groups slide across cosmic distances. Even the Virgo cluster participates in the movement. The cosmic current grows stronger as it approaches that hidden direction. Astronomers gave the unseen center a simple name: the Great Attractor. It was not discovered through direct observation. It revealed itself through motion. Galaxies moving through space carry the fingerprints of gravity. Each measured velocity becomes a clue. Together, they describe the shape of an invisible landscape. Matter gathers in deep gravitational valleys. Galaxies flow toward those valleys over immense spans of time. The Great Attractor appears to be one of the deepest. Yet the region itself remains largely hidden behind our own galaxy. Dust conceals the heart of the structure. Light from distant galaxies fades behind the crowded stars of the Milky Way. Still, the evidence continues to accumulate. Thousands of systems share the same drift. The Milky Way is part of that flow. Our galaxy is traveling through space toward a destination we cannot easily see. And the deeper astronomers measure the motion of galaxies, the larger the structure behind that pull appears to be. The strange part of this story is not the motion. Gravity pulling galaxies together is expected. Mass attracts mass across cosmic distance. The strange part is where that motion leads. Follow the arrows of galaxy motion across the sky, and they converge toward one region, a region buried behind the bright band of the Milky Way. From Earth, the center of our galaxy stretches across the sky as a dense river of stars. Dark dust clouds thread through it. These clouds absorb visible light. Beyond them lies distant space. But through a telescope, the distant space disappears. Stars crowd the view. Dust scatters incoming light. This is the zone of avoidance. Not a place where galaxies are absent. A place where our view is blocked. Yet gravity does not care about dust. The motion of galaxies continues to point there. Astronomers began searching for ways to see through the obstruction. Different forms of light behave differently when passing through dust. Infrared light can slip through more easily than visible light. Radio waves pass through almost unhindered. New telescopes began scanning the hidden region using these wavelengths. Slowly, faint structures began to emerge. Clusters of galaxies appeared where the sky once seemed empty. Massive concentrations of matter lay hidden behind the Milky Way.
One cluster in particular stood out.
It lies roughly 200 million light-years away. Thousands of galaxies gather inside it. The total mass reaches many hundreds of trillions of suns. This structure is now known as the Norma Cluster. It sits almost directly in the direction of the Great Attractor. When astronomers mapped the velocities of galaxies around it, the picture sharpened. Galaxies were not simply drifting toward Norma. They were falling inward along large-scale gravitational currents. Imagine a vast valley carved into the fabric of space. Matter slowly slides toward the lowest point. Galaxies follow those slopes. Clusters merge into larger flows. The Norma cluster appears to lie near the center of one such valley. But even this cluster may not be the final destination. Measurements show galaxies moving beyond it as well. The gravitational basin extends farther than first expected. Here, the scale begins to stretch the imagination. The region influenced by the Great Attractor spans hundreds of millions of light-years. Thousands of galaxies participate in its gravitational field. Entire clusters drift along its slopes. This is not a single object pulling our galaxy. It is a landscape. Gravity sculpts enormous basins in the distribution of matter. Galaxies drift along these gradients like water following terrain. The Milky Way lies on one of those slopes. The local group slides slowly inward. Cluster by cluster, the motion continues. Some galaxies approach the center from distances so vast that their journey will take billions of years. This motion is not violent. It is slow. Yet it is relentless. Gravity acts patiently across cosmic time. One cinematic line emerges from these measurements. The universe is not static space filled with galaxies. It is a moving landscape. Galaxies travel along its contours. The Great Attractor is one of the deepest contours discovered so far. Yet the story does not end with its discovery. Because when astronomers expanded their maps even farther, something unexpected appeared. The Great Attractor itself may also be moving. The flow of galaxies continues past it, as if the valley we discovered is only part of a larger terrain. A deeper structure waits beyond. The discovery of the Great Attractor seemed at first like the solution to a puzzle. Galaxies across enormous distances were drifting toward one region. A massive cluster hidden behind the Milky Way offered a plausible explanation. The Norma cluster contained extraordinary mass. Thousands of galaxies orbit inside it. Dark matter halos surround the entire structure. Gravity from such a cluster can influence motion across tens of millions of light-years. Yet the velocity measurements refused to settle. Astronomers continued measuring galaxy motion across wider distances. Clusters far beyond the Norma region were included in the maps. The expectation was simple. Galaxies approaching the cluster should slow as they fall inward. Eventually, their motion would orbit the central mass. But that pattern did not appear. Instead, many galaxies were still moving past the region. Their motion did not end at the Great Attractor. It continued beyond. Gravity should produce a clear center, a final destination where the motion converges. But the data showed something more complicated. Clusters near the Great Attractor were themselves drifting through space. The structure appeared to be part of a larger flow. The river of galaxies did not stop there. It continued across deeper cosmic terrain. This discovery forced astronomers to rethink the structure of the nearby universe. For many years, galaxies had been organized into clusters and superclusters, large groups bound by gravity across hundreds of millions of light-years. But these superclusters were often imagined as relatively stable structures. The new velocity maps told a different story. They revealed motion across scales larger than entire superclusters. Clusters were not isolated islands. They were currents within larger gravitational basins. To understand this behavior, astronomers turned to computer simulations. Mass was distributed across enormous virtual universes. Gravity was allowed to act over billions of years. Slowly, a pattern emerged. Matter in the universe does not spread evenly. Small fluctuations in density grow under gravity. Dense regions pull in surrounding material. Over time, these regions connect through filaments. Long strands of galaxies stretch across space. Between them lie enormous voids, nearly empty regions where little matter collects. The cosmic web appears. Galaxies do not move randomly across this web. They slide along filaments. Gravity pulls them toward intersections where filaments meet. These intersections form massive clusters. Yet even clusters lie within larger gravitational valleys. Matter continues to flow inward from surrounding structures. The Great Attractor now appeared less like a single dominant object. It looked more like a knot in the cosmic web. A powerful intersection where multiple filaments converge. Clusters fall toward it along those filaments. But the entire structure itself may still be sliding along an even larger gravitational slope. Here, the scale of the problem expanded dramatically. The region influenced by these flows extends across hundreds of millions of light-years. Thousands of galaxies move along the same general direction. The Milky Way participates in this motion. So does the Virgo cluster. So does the Norma cluster. The flow unites structures that once seemed separate. Imagine an enormous landscape carved into invisible gravitational terrain. Mountains represent dense clusters. Valleys represent deep gravitational basins. Galaxies drift across that terrain, slowly descending along its slopes. Our galaxy is traveling across that landscape now. Not by choice. Gravity defines the path. One short truth emerges. Mass shapes motion. But the deeper measurements push the story even further. Because the Great Attractor does not sit alone in this terrain. Beyond it lies an even larger gravitational structure. One so vast that it reshapes how astronomers classify our place in the universe. The Milky Way is not simply part of a cluster. Not even just part of a supercluster. We are inside a flowing cosmic basin. A basin whose scale stretches across hundreds of millions of light-years. And the galaxies inside it are still moving. When astronomers expanded their velocity maps across the nearby universe, a remarkable pattern emerged. Galaxies did not simply form clusters. They organized into vast, flowing systems. Thousands of galaxies moved along connected paths. Clusters that once seemed separate now appeared linked by shared motion. The local group was part of this movement. The Virgo cluster was part of it. The Norma cluster was also moving within the same gravitational landscape. The entire region behaved like a single system. To visualize this structure, researchers began tracing the paths galaxies follow through space. Each velocity measurement became a vector showing direction and speed. When these vectors were plotted together, something striking appeared. The galaxies formed streams. Matter flowed along enormous corridors, stretching across space. These corridors converged towards central gravitational basins. It looked less like scattered galaxies and more like rivers feeding a cosmic ocean. Gravity creates the slopes. Galaxies follow them. One cinematic comparison became unavoidable. The nearby universe behaves like a watershed. On Earth, rain falling on a mountain divides into separate river systems. Each river flows toward its own ocean basin. The cosmic landscape behaves in a similar way. Galaxies inside a gravitational basin slowly drift toward the same deep center. Astronomers began identifying the boundaries of this basin. They traced which galaxies flowed inward toward the same destination. The results revealed something enormous. Our galaxy belongs to a superstructure now called Laniakea. The name means immense heaven. It is appropriate. Laniakea contains more than 100,000 galaxies. Its diameter stretches across hundreds of millions of light years. The Milky Way lies far from the center. We sit along one of the outer slopes. From this position, galaxies drift slowly inward along filaments of the cosmic web. Clusters act like nodes in this network. Matter gathers there before continuing deeper toward the basin center. The Virgo cluster marks one of those nodes. The Norma cluster lies farther along the path. And near that region sits the gravitational center, long called the Great Attractor. Yet Laniakea itself is not a rigid structure. It is a flow. Galaxies are not fixed within it. They move. Slowly, but continuously. The local group travels through this basin at hundreds of kilometers each second. Over billions of years, our galaxy will shift deeper into the structure. The movement is almost impossible to sense from Earth. Stars orbit quietly inside the Milky Way. Planets circle their suns. But the entire galaxy drifts through space as part of this immense current. One short line captures the scale. We are inside a moving continent of galaxies. Astronomers identified the boundaries of Laniakea by tracking where flows diverge. At the edges, galaxies stop moving inward and instead drift toward other basins. These boundaries act like continental divides. Beyond them lie different gravitational systems. Another supercluster may pull in a different direction. The Great Attractor sits near the heart of our basin. But it is not the only massive structure nearby. Farther away lies an even larger concentration of galaxies, called the Shapley supercluster. Its mass exceeds that of many other known structures. Some measurements suggest that even the Great Attractor may feel the pull of Shapley. If true, the cosmic flow continues beyond the basin we first identified. The rivers of galaxies may lead toward deeper terrain still. Here, the cosmic web becomes difficult to map with certainty. Distances stretch across hundreds of millions of light years. Observations grow more complex. But the pattern remains clear. Galaxies move along gravitational gradients. Clusters gather at intersections. Superclusters form enormous basins where matter slowly converges. The Milky Way is part of that motion. We are not drifting aimlessly through the universe. We are following the contours of a vast gravitational landscape. And the Great Attractor marks one of the deepest valleys within that terrain. Yet the final shift in perspective is still coming. Because the true significance of the Great Attractor is not the object itself. It is what it reveals about how galaxies move across the universe. The Milky Way is not merely orbiting inside a cluster. Our entire region of space is sliding across a cosmic boundary. And that boundary defines the shape of our gravitational home. The discovery of the Great Attractor changed the way astronomers think about motion in the universe. At first, galaxies were treated as isolated systems. Clusters formed small communities scattered across expanding space. But the velocity maps revealed something deeper. Galaxies do not simply exist in clusters, they belong to flow systems. These systems behave like basins in a gravitational landscape. Matter slides inward along invisible slopes created by mass. The Milky Way is moving within one of these basins now. The local group travels through space toward the inner regions of Laniakea. Virgo lies along that path. Norma lies deeper still. Beyond those landmarks sits the region long called the Great Attractor. But the true importance of that region is not the cluster hidden there. It is the shape of the gravitational terrain surrounding it. Astronomers now study this terrain using velocity fields rather than simple position maps. Instead of asking where galaxies are located, they ask where they are going. Direction becomes the key measurement. Thousands of galaxy velocities combine to reveal the slopes of space. Where the vectors converge, the gravitational valley deepens. Where they diverge, the boundary of a basin appears. These boundaries are subtle but powerful. They divide the universe into enormous domains of motion. Galaxies on one side of a boundary drift toward one basin. Galaxies on the other side flow somewhere else entirely. These divisions act like continental divides across cosmic terrain. On Earth, water falling on one side of a ridge flows toward one ocean. Water falling on the other side flows toward another. Galaxies follow the same logic. The boundary around Laniakea marks the edge of our gravitational watershed. Inside it, more than 100,000 galaxies share the same long-term destination. Outside it, galaxies drift toward other centers of mass. Our galaxy sits deep within that watershed. The local group lies far from the center, but firmly within the basin. Gravity determines the path. The motion is slow, yet the scale is enormous. The Milky Way travels hundreds of kilometers every second through this landscape. Over millions of years, that movement shifts our position across intergalactic space. Over billions of years, entire galaxy groups migrate along the filaments of the cosmic web. Stars orbit inside galaxies. Galaxies drift inside clusters. Clusters slide inside superclusters. Every layer participates in motion. One impact line reveals the truth. Nothing in the universe is truly still. The Great Attractor once appeared as a mysterious object pulling galaxies inward. Today it is understood as part of a larger gravitational system. A basin where cosmic flows converge. Its mass is immense, but its role is structural. It marks the center of motion for a vast region of the nearby universe. And yet even this basin may not represent the deepest structure. Measurements continue to suggest motion extending beyond Laniakea. The Shapley region far beyond may exert influence on the entire system. If that interpretation holds, then the cosmic terrain stretches farther still. Our basin may be sliding along the slope of a larger gravitational valley. The universe reveals itself layer by layer. Clusters become nodes. Superclusters become watersheds. Galaxies become travelers across invisible terrain. The Milky Way is part of that journey. Our galaxy carries hundreds of billions of stars through this landscape. Planets orbit quietly inside those stars. Civilizations rise on small worlds. All while the galaxy itself moves through the universe, slowly descending along a gravitational slope carved by unimaginable mass. The Great Attractor is not simply an object in space. It is a feature in the shape of the universe. A deep valley in the cosmic landscape. And our galaxy is already on the road toward it. At the beginning, the universe seemed calm. The Milky Way appeared as a vast rotating island of stars. Galaxies seemed scattered across space like distant lights. From that view, our galaxy felt almost stationary, a stable system drifting quietly through the expanding universe. Measurement slowly removed that illusion. The faint glow of the cosmic background revealed motion. Our galaxy is not still. The Milky Way moves through space at enormous speed, hundreds of kilometers each second. And it is not traveling alone. Dozens of nearby galaxies share that motion. Clusters beyond them drift along the same direction. Thousands of galaxies participate in the same gravitational flow. The cause of that motion first appeared mysterious. All measurements pointed toward a hidden region of the sky. Behind the dust and stars of our own galaxy, something immense was pulling. Astronomers named it the Great Attractor. At first, it seemed like a single object, a massive cluster hidden behind the Milky Way. But deeper measurements widened the picture. The Norma cluster revealed part of the structure, yet the motion of galaxies continued beyond it. The Great Attractor was not the final destination. It was a landmark inside a larger gravitational basin. The nearby universe forms a flowing system called Laniakea. More than 100,000 galaxies move within it. Clusters connect through filaments of matter. Galaxies slide slowly along those corridors. Over billions of years, gravity draws them inward. The Milky Way lies inside that basin. Our galaxy is already following the slope. Stars orbit inside the galaxy. Planets orbit those stars. But the entire galaxy travels through intergalactic space as part of a much larger current. One short truth remains. Gravity organizes the universe. Not just inside galaxies. Not just inside clusters. Across hundreds of millions of light years, matter follows the shape of invisible terrain. The Great Attractor marks one of the deepest valleys in that terrain. It defines the direction of motion for an enormous region of the cosmos. Yet even this valley may not be the final layer. Far beyond Laniakea lie other superclusters, other basins of gravity. The cosmic landscape continues outward across unimaginable distances. Galaxies move through that terrain slowly but relentlessly. Our own galaxy is part of that motion now. The night sky above Earth feels quiet. Stars appear fixed across human history. But beyond that stillness, the Milky Way is traveling, carrying hundreds of billions of suns through the universe, sliding along the contours of a gravitational world far larger than we once imagined. The Great Attractor did not merely reveal a hidden cluster. It revealed the shape of our cosmic home.